looking at section 5, least squares regression to variables. This is something we'll look at more carefully in, I forget what chapter, but way up there in section 12, somewhere in there. And but this is an introduction because it's basically more on displaying data, and it's called bivariate data. So this is chapter 3 in in Mendenhall. And take a look at that. It's the first part is really just how you display data. If somehow you have a correlated data set. So basically what you end up with is ordered pairs. So if you have a bunch of ordered pairs in your data set, x1, y1, x2, y2, etc., 2x and yn, then you can display the data in a certain way. That's really all it's talking about for the first part. Then we get into scatter plots and regression analysis and correlation. That's important, and this is just an introduction. This should go, don't spend way too much time on this yet. We'll save it for later. But I'm going to show you how you do this in Excel, and that'll be the next video, and just the basic concept. So here's the basic idea. So suppose you have a bunch of data points, and you can graph those data points on a number line. So x, y, and let's say, let me go and change my font here. Suppose you have a bunch of these data points. Look like that. And what you can do is the actual values of each of those, and you do this process. It's called least squares regression. And then you can get a line that basically goes through those. And that line is it's kind of like the average of all the points. And so that, if you can show that, then you say that there's some sort of correlation between the lines, between the data points. And so we need to know a little bit about the graph, a little bit about the line in general. So I'll do a brief review of that and what that looks like. So this is a short review of lines for algebra. We'll start off with y equals mx plus b. So m is the slope, 0b is the y-intercept. Hopefully this is familiar. The way I drew that, it looks like it go right through the origin. That was a little fluke. I just sort of guessed. But if you have a line that goes like that, then this would be, of course, the intercept crossing the y-axis. And I just kind of guessed on that line, but there's a way to look at all of these distances and averages like this. And I'm actually not going to make you calculate that. I just want to show you how it's done, and then we'll use computers to do it. So you want to be able to use Excel. It can be done that you can get what's called the correlation coefficient on your calculator and other packages. So I'll ask you to do something on that. But that's the regression analysis concept. So that's a scatter plot that you can just literally plot them so you would set them up as an x, y, and you do your x values and your y values. So this first one would be like your, actually it looks like x2. So x2, y2. This first one would be x1, y1. This one right here would be x3, y3, etc. So that's what it would look like. Okay, let's see. So m is the slope. A couple details about that just to refresh your memory. That is the change in y over the change in x. Rise over run would be another way to describe the slope. So how accurate the slope is and what it looks like is going to mean something for our future work. Okay, so the real question is, when you have this regression analysis, the question is, how close does the data represent a line? So that's the question for regression analysis for data. Now that's for linear regressions. It means what you would say is that there's a linear relationship between the data points. It doesn't have to be linear. You could have a bunch of data. So let me just show you some just basic examples. You could have a bunch of data points like this. Let's just do a couple here. Let's just do that one and this one. So you could have all these two data points x, y. This one, so you could have one that's just not correlated at all. Like you could have something like this. Let's change the color just for fun, huh? Okay, let's do green. So you could have just a bunch of data points like this. Well, there's no correlation for that one. You could have something like this. Well, that one might be exponential, might grow really fast as you go up. So this one could be an exponential curve. Then you can have different ones that are like a polynomial curve, like a parabola, like it goes down and goes back up. So this concept of regression is really just the case that it is a linear correlation. And you'll be able to calculate that correlation based off of the information, and then be able to report what it is. Now, for now, I'm just giving you an introduction. This is the concept we're looking at for this stuff. Okay, so let's do some of the detail measurements. Let me show you this. Bring this back down to 3. And to measure, okay, so we use what's called the correlation coefficient. Correlation coefficient. So R, you'll be looking at R, and that is equal to, and I'll have to define all this stuff for you, it's S sub xy divided by S sub x, S sub y. So so you have a bunch of data points for x. We're going to go back here, right here. You have a bunch of data points for x, and you have a bunch of data points for y. And remember, the last thing we did for one of the videos is the sample standard deviation. So S sub x is the sample standard deviation for x. S sub y is the sample standard deviation for y. S sub xy, I haven't defined yet. Okay, so that's what this is. This is what's called the covariance divided by Sx, Sy. And so Sxy is defined to be this. you basically take the sum of all the differences and then you multiply them. So it's the sum x sub I minus x bar times y sub I minus y bar. The sample means divided by n minus 1, right? Because anytime you say sample, you divide by n minus 1 for the for the standard deviations. So that's the numerator of R. And basically this R will tell you like how close or how significant it is to be a linear relationship or not. Like, is it correlated or not to linear? And then, so also notice that this calculation here does not make it positive. So these values, when you do all this and the sum, it could be negative. So you actually have R's that are positive and negative. So R is actually between, and this is stuff I'm not proving. I'm a pure mathematician, so I'm a little skeptical of some of this stuff when I don't prove it. R is between negative 1 and 1 when you do this calculation. Okay? And that is not obvious. You'd actually have to show that. It has to do with the triangle inequality and things like that. But don't worry about that. All right, so if R is 1, then all points are exactly correlated. So let's just say the closer, this is a statistical term, not a math term. This is where it deviates from mathematics. The closer R is to 1 or negative 1, I'll just say, we say the more the data is correlated. And that's where the real issue becomes, is many times you'll see news agencies and people and, colleges state about correlation, but the causation is never really discussed. You can show things are correlated, but it's really difficult necessarily to show it's the cause of it, it's the causation of it. So to show a correlation is one thing, but to show the cause is another. So let me just give you an example of correlation and causation. Let's say that you can show that eating certain types of food, let's just make one up. So I like sushi. So suppose you can correlate that eating sushi is correlated to longer lifespan. So the question is it really the fact that you're eating sushi, or is it just the people that would have that lifestyle that eat sushi is the cause of it? So you can show correlation, but what's really the cause? Another one I've recently heard of is for longer lifespans, to stay on that same vein, those who have relationships that are more intimate, like you have friends, you have a spouse, you have people that would trust you, that would call someone. So those who have an intimate relationship with people have a longer lifespan than those who don't. So what's the correlation versus the causation? I don't know. I mean, it's correlated. You can show that that's a correlation. But what's the cause? Is it that people will, make phone calls and call the ambulance? Or is it that those who have intimate relationships, and I mean intimate in the broad spectrum of intimacy, is it that those people who have that are more apt to be more positive? Maybe it's their positive outlook on life that causes the longevity of life. You don't know. So you can show correlations, but the causation is often more difficult to really flush out. And that's where we talk about the concept of lurking variables. Variables that you didn't account for that cause the correlation. So lurking variables idea is important. So I want you to start thinking about these things when you see statistics or hear statistics and they say, hey, this is correlated. Well, that may not be the cause at all. So that's kind of what we're coming from, or I'm coming from, in terms of how you want to interpret things. Okay, so moving on to the actual math stuff. Let's see where we're at. Let's do an example. And I think this example I'm going to try to do this on Excel, and I'll show you how to do it, and it'll just do the calculation. So I'm not going to actually even show you this calculation because I don't need you to do it. We'll just do computer stuff. Then later on, we'll talk about what these mean, the meaning behind more of this stuff. I think that'll be good enough. So let's get through section 5 pretty quickly. Just basic ideas, scatter plots, which I just did. I just showed you. You just plot a bunch of stuff. Correlation, and then I'll show you D, and then try some problems. Okay? I think that'll be good.